All right, it's time once again for the SMC Journal podcast. This is a show where it's all about software engineering, performance, DevOps, security, and hardware performance, which is what we're going to talk about today. I'm Scott Moore, your host. Thank you for joining me. Before we get started, let's talk about the sponsors that make this show possible for you. This podcast is sponsored by Saltworks Security. For almost 10 years, Saltworks has delivered world-class application security services and products designed to help enterprises secure their applications from policy to production in an ever-changing security landscape. They're the makers of SaltMiner, an application security management platform designed by security professionals for security professionals. SaltMiner aggregates and normalizes the issues found by many different solutions and enriches that data with business context. SaltMiner gives team members from the C-suite, security, and development teams the ability to manage their application security program through customizable views. The Saltworks SaltMiner Community Edition is a free penetration testing management and delivery application. It provides teams with custom reporting for potentially thousands of end users, red team support, and the ability to manage new and retesting of engagements. SaltMiner Community Edition also allows teams to enforce both testing methodologies and custom vulnerability databases for consistency in engagement delivery. Check them out today at saltworks.io. Okay, this is actually going to be a really cool show where we're going to get down into the weeds. So all of you performance engineering nerds out there, you're really going to enjoy this show because we're talking about hardware performance, specifically around NVMe drives, SSD drives, and storage drives, and why the storage component of the infrastructure is vitally important now more today than ever. It used to be that the CPU was king. That was the thing that was always waiting on everybody else. Well, things are speeding up in other areas. You know, you've got faster RAM now, you've got faster storage, and these are required for a lot of today's new applications, which we'll discuss. So I really wanted to talk about some advancements that have been made in some of the infrastructure components, and that led me to talking to Kelly Osborne of GRAID Technology. So I want to bring him on today's show to talk about some of the advancements that they've seen in terms of SSD drives, NVMe drives, and RAID capabilities. Let's do that now. Hey, Kelly, welcome to the SMC Journal podcast. It's good to have you today.
Thanks, Scott. I appreciate the opportunity to have a little chat this morning.
So tell me about yourself and your company, GRAID.
Sure. So my name is Kelly Osborne, as you saw, and I am the Senior Director of OEM and Channel Business Development at GRAID Technology. I am personally based up in Marietta, Georgia, and our company is headquartered in Santa Clara, California, and we're a software company.
But you work with hardware solutions that make hardware faster, is that right?
Absolutely. That's our goal in life, is solving some fairly well-known issues within the back-end storage arena, which affects performance of everything.
So I noticed that you have a white paper out here called Performance Comparison of RAID 5 Solutions for PCIe Gen 5 NVMe SSDs. Now that's a lot of acronyms. That's a lot of words that maybe some of our audience might not understand. Can we kind of talk through this? What is Gen 5? What's the significance of NVMe SSDs? And why is this paper talking about something performance-wise that's such a big deal?
Well, so think of PCIe as really the serial bus interconnection between your computer and peripherals. And if we go all the way back to the good old days, you used to have a port that your mouse would plug into and a port your keyboard would plug into, and then you had a parallel printer port, and then you had a SCSI connection for your hard drives. And all of these were proprietary independent buses. And the industry wanted to simplify everything, and so we started settling on this interconnect standard called PCIe. And each generation has a label. So we've gone through Gen 1, 2, 3. The prevalent generation that's out there now is 4, and 5 is coming, and we're starting to see servers made with 5. And essentially what you see with this is everything now connects via PCIe, which has made it much more simple to create add-in cards and graphics cards and all of these kinds of things. The issue that we're having is the doubling of performance every time there's a new generation. So a single PCIe Gen 5 by 16 slot can generate up to 64 gigabytes a second, and that's big B, not little b. So it's extremely fast. And really, it's almost always pretty much contained within the server on the motherboard. And so the storage technologies, which are the hard drives, which have now become SSDs, and we used to hear about SAS SSDs and SATA drives and all this kind of stuff. Those were all different kinds of interconnects. But now NVMe has standardized as well on PCIe as its connection to the computer chip inside a server, for example. So NVMe stands for non-volatile memory express, by the way. So
I just built a server myself and had an NVMe drive put in there, and it's super fast. And it doesn't generate a lot of heat. There's a lot of advantages for using them as well. I want to bring up this document here again that talks about the Gen 5 bandwidth, and it talks about Gen 3, Gen 4, Gen 5. Why is this significant?
Because when you take a look at this bandwidth, this is the speed that a drive can send the data. And so if you think about NAND flash, which is the chip substrate that's inside of a solid state drive, the method that it's communicating to the server in the past has been a bottleneck. So the flash was much faster than the interconnection PCIe Gen 3. It's much faster than PCIe Gen 4. It's still faster than PCIe Gen 5, but now a single flash drive, NVMe flash drive, can communicate with your CPU at 14 gigabytes a second, and that used to be 4. And so what we're starting to see is a problem where when you put faster things inside of a computer, you always expose the next slowest thing.
That's right.
So most people aren't getting anywhere close to that theoretical performance in terms of throughput in IOPS or IOs per second. And there are a number of reasons for this. When you start thinking about server type environments, which, you know, if you're running an EC2 instance in the cloud, it's actually running on a physical server somewhere. If you're on-prem inside of a VMware or a Windows server running SQL or Linux, that physical hardware tends to be set up so that you have a lot more data than you have on one drive. So we have to group drives together into a set to create a much larger data space. Well, when you do that, the next thing you have to think about is, how do I prevent a drive failure from bringing my whole system down and then losing data? And we do that with a technology called RAID, which is redundant array of independent disks. And so what's actually happening is you might have 5 drives in what we call a RAID set, and the data is striped across those as it's written. And then parity information is calculated. So there's a couple of different RAID levels. And when you do parity-based RAID using Reed-Solomon algorithms, those are mathematical calculations, and it generates a checksum and a parity bit, and you can stripe that as well. The whole effect of this is, if I lose a drive, I can read the parity bits on the remaining disks to recreate and rebuild the data that's on that failed drive, and I can still be up and running, you know, while that happens. That technology, the RAID technology that we're accustomed to today, has not been able to keep up with the increase in speed of NVMe and PCIe.
Can you talk about how somebody using like software-based RAID, that's really just killing their performance on a computer versus what you're trying to do here with the GRAID solution?
Yes. So, you know, in traditional software-based RAID, you actually are running all of those calculations on your CPU, and it's running in the same space where your applications are running. So it's loaded up in the operating system. And as the drives get faster, and as you increase the number of drives in servers, and we're starting to see server platforms with as many as 40 drives in a single 2U machine, the potential performance there, if you multiply 40 by 13 or 14 gigabytes a second, is massive. What you find with software RAID is it just simply can't keep up. And what ends up happening is the CPU utilization goes so high that you try to get better performance out of those NVMe drives at the expense of CPU cycles and cores, which impacts your applications. So you might have paid for a certain number of licenses from an application like a database, and you're not even getting anywhere close to the performance that it's capable of. What most users do with things like Linux MD80M, which is one of the RAID technologies that comes with Linux, in this scenario, is they'll end up just running what's called RAID 10. And RAID 10 is where I take half my drives in Stripe, and then I take everything I wrote to those drives and mirror them to another set. So if I have 16 drives, I'm only going to get 8 usable drives in terms of capacity. So I have to sacrifice a huge amount of space to do RAID 10. And the only reason you might want to do that is for really, really high reliability, because obviously my data is completely mirrored. And the other reason to do it in software RAID is because it reduces the impact on the CPU, because now it's just doing 2 writes instead of having to do parity calculations, which is more intensive mathematically, right?
Right.
So it does not scale. So, when you look at our white paper, what we did is we actually calculated the theoretical performance and throughput of 16 Kioxia Gen 5 NVMe drives. And then we tested hardware RAID and software RAID, and then our technology to show which has the least amount of impact in terms of the total performance. So that's how we were able to show the difference in our technology.
Awesome. All this sounds really good. As a performance engineer, I'm all about let's make it scale better. But what are some real world use cases that we can talk about where this matters a lot?
So, it's a lot to do with doing more with less. If you are in a large HPC environment, for example, high performance compute. So we get into these very large supercomputer environments where you have a huge file system, hundreds of terabytes of data, and generally they're going to use a parallel file system, something like Lustre, which is an open source one. There's another one called BGFS that's real popular. And what that does is it actually, takes the space that's in one server, and then it adds it to 5 or 6 more servers. And so you get what looks like a much larger amount of capacity. And then the data, that software knows where to write the data. And the problem is, if I don't do RAID protection of the drives in those individual storage nodes, one node can take you down. So when you impose some sort of software RAID, once again, you end up reducing the performance of that environment. And when you're running jobs that take, let's say, a month, we're talking about things like particle accelerator type applications in the Department of Energy. When you have a job that literally takes a month, if you have a glitch, a failure of any kind during that period of time, it's a pretty expensive proposition when you have to start back at the beginning and start all over again. So HPC needs protections to prevent that from happening, but it has to be done without impacting performance so extensively. So the bottleneck problems of software and hardware RAID have been solved with what we're doing. That's an area. The other one is things like media and entertainment, video streaming. So if you're in an environment if you watch car racing, we were talking about that earlier. If you watch car racing, it's one thing to see that broadcast on your screen. You can now log into things like NASCAR.com and be a subscriber. And during that race, I can actually stream from inside the car. Well, if I've got 40 cars running around that track really fast and they're all streaming 8K video, how much hardware do I have to have on the back end to capture all that real time and then turn it around and get it out into a web environment where you could actually watch it without, having so much latency, you're 5 seconds behind real time. So speed is of the essence for that. The other thing that's of the essence is, how do I reduce the footprint of hardware I need in that type of scenario? And if I can do 10 cameras per server with the old technology, but the new technology can do 50 cameras per server, you can handle a lot more with less back-end equipment. So those are things. And then very, very high frequency trading type apps, low latency applications. So when you think about some of your viewers might be users of things like Redis or databases like MySQL and, Couchbase and MariaDB, and these high performance databases or Oracle, speeding those up. And especially when you're talking about high frequency trading and how important that is to be the fastest you can be.
That's something you brought up. I wanted to mention that you have another white paper that was just released about offering Supreme RAID. This is some technology that you're offering that gives you higher performance as an alternative for database workloads around things like MySQL when you compare it to Linux-based RAID, right? So can you talk a little bit about Supreme RAID?
Yes, so Supreme RAID is actually what we call our product. And what we've actually done is written a software RAID stack that instead of running on the CPU inside of your server, the Intel or AMD chip or ARM, if you will, we actually take that software now and run it on an NVIDIA GPU. So we all know how fast NVIDIA cards are because they have lots and lots of parallel processing cores called CUDA cores. Some of them also have tensor cores and things. And we've been able to take that mathematically challenging application that has to compete with your applications in the Linux operating system, and we offload that now from the CPU and we moved it to a GPU. We also take advantage of something called peer-to-peer DMA, and we allow the data on the NVMe drives to communicate directly with the operating system without having to flow through our card. So we do not limit you to the number of lanes we have on our card. So I talk about lanes. Think of PCIe Gen 5 has 16 lanes for one connection. So our card is a 16 lane connection. If you have 20 drives, there's 4 lanes per NVMe drive. So you would have 80 lanes. And the problem with hardware RAID traditionally has been all of those 80 lanes have to funnel down to 16 because everything goes through that physical hardware card. We have a way around that that keeps our card out of the data path. So we're just using it for command and control and the mathematical parity calculations for the RAID. And so we're able to get very, very close to the theoretical throughput performance of those drives. And that impacts things like databases because how fast you write data, how fast you read data. Some of these databases and key value databases actually run partially in memory or in memory, and data sets are getting bigger, and it becomes very expensive to run everything in memory. So you need a very high speed flash layer just beyond that for these databases. And then secondly, by taking that processing off the CPU, you've left that entire CPU there for the database application itself.
I think a lot of performance engineers in the audience that are watching this that are hardcore into the infrastructure are going to be very interested in this. How can they contact you or find out more about this technology?
Yes, so it's graidtech.com, GRAID.com, and our white papers and other documents and podcasts and things like this are all available there. And we work through a number of partners, so we sell through various resellers in the market. We also have partners like Supermicro that are actually selling our products now as part of their server build. So we call that an OEM, original equipment manufacturer. And I believe, it's really interesting because some people thought they were done with infrastructure, but we're seeing a lot of repatriation of certain apps. I think the corporate world swung to the cloud pretty heavily, and what they're finding is there are certain applications that just aren't suited for that.
Right.
So it has to do with the cost of ingest and egress of data itself. If you have huge data sets and you're copying it and then reading it back in, they charge you quite a bit for that. So we're seeing certain applications, really low latency applications and intense data type applications are being repatriated on-prem. And so there's a lot more interest now again in on-premise data center hardware and infrastructure. So we work with a lot of partners that are involved in that technology. And you're also welcome to send me an email at kelly.osborne@graidtech.com.
We'll make sure that we include the links to the site and the white papers as well. And this is all really good news. And repatriation is something that we are talking a lot about on the Performance Tour as well. A lot of people, the subject keeps coming up because of the cost optimization that's needed today. So, Kelly, thanks so much for being on the podcast with me today. It's always good to talk to you.
Absolutely, Scott. I appreciate it. And congratulations on your anniversary.
Thank you. All right. I love talking about hardware and infrastructure as much as I do any of the other components that make applications faster. But those are the basic building blocks, right? So I think it's important that even if you stay in the software realm or you're a developer that's just trying to write high performance software, code, you should still be aware of those underlying things that are supporting you, that basic infrastructure, and know how all of that works. And I think that's key to understanding how to make the end user experience the best that it can be. What do you think? I'd like to hear your feedback. I'm very easy to reach on social media platforms. You can scan that QR code, which will take you to a bio page where you can find out how to reach me on LinkedIn, Twitter, Instagram, and other places. You can also reach out to me by email by using the email address heyscott@smcjournal.com. Would love to hear from you. Also, if you like this video, if you could give it a thumbs up, like, and maybe become a subscriber to our YouTube channel, that would really help me out a lot, help to train that algorithm. Until next time, this is Scott Moore saying thank you for watching the SMC Journal podcast with me, and we'll see you next time. Bye-bye.